So good afternoon, everyone. My name is Lauren Aki, and this is my area exam, Advancing Robotics with Vision Language Action Models. So we'll start with this core motivating question. Can robots learn to act from the same models that understand language and vision? So if you give our friendly robot here a visual of its environment, whether that's through camera data or LiDAR data, or any type of other sensor, and then you give it a natural language instruction, can the robot actually figure out what actions to take given these inputs, and can actually just go ahead and execute those actions without needing any type of intermediate steps? So prior to vision language action models, a lot of the development in robotics happened in more discrete areas. So you would have camera systems that understand images and can process images. And then you would have language systems that can understand and generate text. And then you would have your low-level robot controls, which would figure out how to actually move the robot. And these all were working okay separately, but chaining them all together can make your system more brittle. So if we can move to a model where we go directly from perceiving and sensing right through action, can we actually get better robot performance by doing that and with less brittleness in our system design? So this is what we're going to talk about today. We'll start with some early models. This is where we ground a language model in the robot's capabilities. Then we'll show that the vision language action paradigm works, and we'll scale the vision and language components and see what we can get from doing that. And then we'll look at some open source vision language action models and see how competitive they are with less parameters than some larger scale proprietary models. After that, we'll move into new ways to actually produce those actions. So can we actually get smoother trajectories or continuous controls rather than kind of jerky robot movements? And following that, we'll move into some hierarchical approaches. So these are combinations of models to improve the long horizon task success and our task compositionality, which means our ability to chain skills together. And we'll take VLAs from manipulators to legged robots and see what kind of things we can do there. After that, we'll talk about chain of thought, which is where we take some of the lessons from large language model development, and we try to do intermediate reasoning before we take action as part of the VLA. And then finally, we'll wrap up by talking about some open research questions for autonomous exploration using these vision language action models and what we can hope to do by exploring that. So we'll start with early models. This is the Say Can paper, Do As I Can, Not As I Say, Grounding Language in Robotic Affordances. And this paper comes about because the authors recognize that you can get a large language model to tell the robot what to do. But the model has no way of knowing whether or not the robot can physically do that given its capabilities. So what if you could combine what the language model says with what the robot can actually perform given its physical embodiment? And so they construct a system where they create a predefined skill library. These are natural language skills like find an apple, a simple skill list. And for each skill, they train a policy network such that the robot can actually execute that skill. And then they also have a value function, which given an input image, tells you how likely the robot will be to succeed in that skill, given the visual inputs. So at inference time, the user would ask a question like, how would you put an apple on the table? And the model would go ahead and take the skills dictionary that it has, try to match that up in terms of relevance to the user prompt, assess the value function, like how likely the skill is to succeed, and then the combination of those is the probability of success for that particular skill. So whichever skill received the highest score would be the one that the robot executes. And they actually showed really impressive performance at the time with this model, getting it to do pretty simple tasks, but in a kitchen environment and in a real-world scenario rather than just in simulation. But you can imagine that if you have a fixed skill library and you have to train a policy network for each skill, and you need a value function for each skill, that as the number of skills grows, this isn't going to scale very well because you'll be retraining for each new skill that you add to this library. So what if you could eliminate this kind of handcraftedness in this type of model and train one model that learns to output robot actions for a variety of skills? And that's where RT1 comes in. This is Robotics Transformer for real-world control at scale. So this is a work that came out of Google DeepMind. It's a transformer-based robotics control policy that takes visual inputs and a natural language instruction and then directly outputs robot actions. So they were able to show with this that they could do hundreds of tasks with a single unified policy versus having multiple different policies for every different skill. And they were also able to show some generalization capabilities across semantically similar instructions. So rather than having to explicitly say, put the towel beside the sink, the model could understand that move the towel near the sink and put the towel beside the sink have a very similar action output because they're roughly the same skill, semantically speaking. So when we look at the action outputs here, all of the actions are discretized into these bins. So you don't have the full expressive control of the robot. You only have fixed discrete bins for actions that you could take. Now, this was a very long effort to collect all of this data. So it involved teleoperating 130,000 episodes from 13 different robots. And they got a 97% success rate across 700 skills. But about this time, we're starting to see large internet scale pre-trained models come about. And so you start to wonder, can you get better generalizability? Can you handle even more skills or adapt to different types of robots if you're able to use these pre-trained models instead of building your own? And so they come up with kind of the next level after RT1, which is RT2. This is vision language action models, transfer web knowledge to robotic control. And with this model, they're able to take internet scale visual question and answer data sets and add that to the robot action data that they've collected through teleoperation. And they co-fine tune this model that's a combination of a vision transformer and a large language model, which now is outputting actions in the like language tokens of the model, and then detokenizing those, but still into discrete bins of robot actions that are possible. And they're able to do this all closed loop. So it's a pretty exciting next step. But this was all closed source from DeepMind. So there's reproducibility and adaptability and scientific transparency that's lacking here. So what's an academic researcher to do when you can't access big models that Google has? And that is create an open source version because you can. So this is OpenVLA, an open source vision language action model. And this follows a very similar scheme to RT2, where you take an input, an image input, and a language instruction. You put that through a series of modules to tokenize them, and then you put them through, in this case, Llama 2 7 billion parameter model, and it outputs, again, tokens in the language kind of vocabulary that get detokenized into these discrete robot actions. And you might think like, okay, well, what's the big deal? They just did what Google did, but actually they did it better. So they achieved a 16.5% absolute improvement in task success over the RT2 field of models, and they did it with less parameters. So they took it from a 55 billion parameter model to a 7 billion parameter model.
Question, what made it better?
So instead of, they basically just changed the architecture of what does the tokenizing. So they got a lot better performance by using a combination of Dino V2 and SIGLib to actually encode the vision inputs rather than in the previous model, which was just a VIT. And I forget which actual model they used in RT2, but I think most of the performance actually comes from better image encoding and tokenization here.
So in the VLA, they have a better V.
Yeah.
Okay.
Yeah. So we just looked at ways to ground a language model in the robot's capabilities, and we looked at scaling vision and language components. But now we're going to look at some new ways to produce action outputs so that we can get smoother trajectories and smoother continuous controls. So all the work until this point, we've had action outputs that are fixed to discrete bins. And this means that we're losing some fine-grained precision or continuous control that we would probably want in our robot systems. So we're getting kind of like jerky, low-resolution movement, and that's not going to be suitable for every robotics task. So how can we get smoother action outputs? And then what do we do when there's a multimodal distribution? So if you have multiple valid grasps of an object, for instance, how do you handle that with these action outputs? And that's what we'll talk about for these new action paradigms. So one of the first papers to handle this is Octo. This is an open source generalist robot policy. And in this model, this is where we're starting to see generative modeling techniques start to get applied to control problems. So rather than using a discrete action output head, they switched to using a denoising diffusion output head. And with denoising diffusion, they're able to capture multimodal distributions, and they're able to get continuous controls instead of having to discretize all the actions into discrete bins. So if you aren't that familiar with diffusion, the idea is that you train a model to go from noise down through a series of denoising steps to coherent action outputs. Another interesting thing that they come up with for this architecture is that they decouple the transformer from the action head. So you're able to scale both independently, and that turns out to work for a really interesting use case. So prior work scaled the vision and language components, but they left the action policy somewhat underdeveloped. So what would happen if we scaled the action expert in addition to scaling vision and language? And that's what DEX VLA, this is Vision Language Model with Plugin Diffusion Expert for General Robot Control, does. So on the left-hand side, they have this kind of architecture and embodied curriculum learning. This blue box right here is the diffusion parameter expert that they've scaled. But I'll have you actually focus just on the diffusion expert for now. So they take this concept and they scale this diffusion policy up to a 1 billion parameter transformer-based model. And they use this multi-headed design where each action head on the model corresponds to a different robot embodiment. And so they're able to actually deploy this onto multiple different types of manipulators and still see that the model succeeds. They compare to Octo and OpenVLA, two of the models we've looked at, and they get a much improved task success in some of these easy tasks like shirt folding, bin picking, and bussing tables. These are becoming kind of the common metrics for some of these VLAs that are manipulator-based. But one of the really interesting things that they discover is that they're able to learn several skills on new embodiments with less than 100 demos. So in many of the prior works, they needed thousands of teleop demonstrations to actually enable the models to get the robot to learn and complete the skill. And they were able to show that with this scaled action expert, they could do more with less. And we like less robotics demos because it's less painful for us to collect. So this was a pretty exciting result that came from this paper.
Quick question. What about action representation? Are they using?
Index VLA.
Yeah.
I think they're still using just the quantized actions that come out of this.
Delta X, delta Y.
Yeah, but I haven't.
When they use fewer examples, how do they analyze how generalizability works? Like, do they change different configurations for each one of these tasks and
I think they
demonstrate any sort of
deployed to completely new of a similar style of robots. If you had like two different bimanual robots, they would deploy to a new one that they hadn't trained on and see how it worked with only a few demonstrations.
Are there any like standard evaluations for these types of tasks across the community?
From what I've seen, it's starting to form, but hasn't quite materialized into a fully standardized benchmark.
Basically just like vibing their evals.
Yes.
Okay.
It might be one step above vibing their evals. I feel like that might be like
one step worse.
Yeah, I think it's one step.
I mean, it could be, not vibing, it could be cherry picking.
I think it's safe to assume that looking at the citation dates, right? Like 2024, 2023 is like the oldest one you're covering really so far.
Yeah.
Like there's just not, given the publication lag time, like nobody's even going to propose something, let alone justify it.
But even if you're looking at here, right, also 15% success rate. Yeah, but the
What does that even
usually,
mean?
yeah, exactly. Is
Okay,
that when you
yeah.
think your paper didn't work?
Yeah, that's like, I mean, I've written papers like that. So it's not like I'm saying I don't understand, but it's like, okay, anyway, thank you.
Okay, so we looked at, sorry. So we looked at scaling up this diffusion action expert to get continuous control and long horizon capability. But if you've worked with denoising diffusion, then you'll know that it's kind of slow at inference time. So for denoising diffusion, the nature of it is that you can't really get away with not doing all the denoising steps to get a coherent output. So you're having to do that at inference time. And you start to wonder, can we get faster continuous outputs somehow? And that's where Pi0 comes in. This is a vision language action flow model for general robot control. And this builds on a pre-trained VLM and then adds this 300 milliparameter action expert to that model. So for this, they introduce something called flow matching instead of denoising diffusion. And with flow matching, you're still learning to go from noise to actual outputs. But instead of having to do a stochastic denoising process, the flow matching objective is to learn the vector field for the data that you're looking at. So it learns how to transform a noisy sample through an ordinary differential equation into the actual outputs that you want. And this means that you're not kind of limited by needing to do so many denoising steps. And because of that, you're able to get much faster control outputs than diffusion, and you still get those smooth trajectories that you want for your robot. So again, they compare to OpenVLA and Octo because that's now become kind of the standard. And they use these similar tasks like shirt folding and busing and grocery bagging. DexVLA came out. Some of these come out on archive long before they actually come out in their peer-reviewed state. So sometimes it's not easy to tell which one came out first. But the performance is around that of DexVLA for these types of tasks. Even though they saw a really good performance improvement here, they still mentioned that action language misalignment was a core bottleneck for them. So they mentioned three things. One is semantically mismatched trajectories. So they noticed that the model could get confused when it had objects that are visually similar, and it would actually do the wrong set of steps going for this object that looked like the one it was supposed to get. They also evaluated this in an open loop fashion, so there was no feedback going in kind of correcting the model, and that meant that errors tended to accumulate and become worse and worse and worse over long horizons. And then the last thing they noticed was poor long horizon compositionality. So the model was really struggling to chain together sequences of skills that it didn't see in its training data.
Just because of training data?
I think it has more to do with maybe an open loop evaluation than just the training data.
I thought it was context window.
For
Pi0, like vision language, they could only handle tasks that were like 2 seconds long or something because of the frame rate of image inputs. And like you basically blew through 32,000 tokens too quickly. Was it their data input or was it their inference?
I thought it had more to do with this combination of evaluating it in an open loop fashion and seeing it drift. And then by the time you've drifted, it's like maybe the context has changed from what you would have been able to get.
You can't even fork because
now you're out of
tasks,
yeah.
And so like, all right. And was there any like mechanistic interpretability evaluation inside this too, or no? Like when you mentioned that they couldn't figure out which cup or which object to handle or something like that, did they like look at the activations on the vision tokens to see or no?
I don't recall them talking about that in the paper if they did do that. Okay. It sounds like this was their first like trial of this, and they didn't do a lot of that kind of mechanistic analysis.
Yeah.
I had a question about the graph. If you know whether average task progress is analogous to the score from the DexVLA paper, because the graphs look the same, like if you kind of blur your eyes, like the
But yeah, but
are shown the same shape.
Yeah.
But they say average task progress, like 0 to 1, and in Dex VLA, they have like a manual scoring rubric for each of those tasks in the appendix of that paper.
yeah, I'm actually not sure if there's a difference between those.
How do they define task progress? Because right now everybody's moving towards this idea of it's a recovery from errors and mistakes. So rather than telling you the success rate, I'm gonna tell you how far I went throughout the process, right? But that's gonna move in the target a little bit
Yeah,
because prior work didn't do it. So what does it mean that Octo has 0% average task progress in that?
so for this, they said that Octo and OpenVLA in many of the tasks struggle to do basically anything. They
So
couldn't
it's
get
like
them
a
even
base.
to start.
Yeah, exactly. Like
Um,
the baseline doesn't compile, so I put a 0 there, right?
yeah. I mean, I can understand the criticism there for sure.
But could cursor get it to compile?
Yeah.
Moving on. Moving on.
So we've just gone through scaling our vision and language components for these
So
VLA
actually,
models.
sorry, I actually had a question. How do they define the progress? That's
Oh.
progress in there.
For here,
Do they have a definition, or is it just a vibe in that too?
I think they might have vibed that too.
Okay.
Like percentage of
But I think
Yeah, exactly.
project steps before they decided that something had to be
yeah.
done.
And I think that comes down to how they've broken down what that task sequence looks like
Okay.
before they determine the success of it. So if you get to like, I've at least folded the sides of the shirt, they might consider that like, oh, that's half the
20%,
task.
yeah.
Yeah, you know.
They do on the website actually not use average task progress, but they use score, normalized score. So they might actually mean the same thing. It might just be the score from the rubric before, but they call it
But they
something
call
else.
it something else.
But we could.
Okay.
All right, so we looked at the early models, so we've seen kind of how this vision language action paradigm can work and some options for scaling vision language and even action outputs. And we looked with new action paradigms at getting smoother trajectories and continuous control. And now we're going to look at some hierarchical approaches, and these are combinations of models that are put together in some different ways to try to improve the long horizon task success and try to improve task compositionality, since that's still been a struggle from earlier models. We'll also take VLAs from manipulators to legged robots for the folks in here who are interested in seeing how that can work. So what if we could combine these models, combine different combinations of models, and get better generalization and long horizon task success? And we'll look at a few approaches to that. So the first one is Pi-05. This builds on the Pi-0 model. But for this, they start to break it down into a pre-training and a post-training and inference stage. So on the left-hand side is the pre-training stage. And in this stage, they get human annotators to provide bounding boxes, language subtasks, and they discretize the action space so that they can make training faster, because it is faster to train a VLA using discrete actions. When they go to the post-training and inference stage, they go back to using this type of action expert that uses flow matching to generate the continuous action outputs. But they break up the inference stage. So they have this model first predict a high-level subtask from the user prompt and the input images, and then a low-level action sequence conditioned on that subtask gets used for the action expert. So they do this in an attempt to try to improve generalizability. Like if you take this model to a place the training data doesn't cover, can it actually do better? And they find that it does do much better than their prior work, Pi-0, and then a number of the other baselines when they break it into home environments that it's never seen before. So this actually improved the kind of zero-shot generalization in some of those unseen environments that weren't part of the training data. Now that's all well and good, but we've seen really simple skills so far, and we haven't seen a lot of talk about complex prompts or user engagement with a VLA. Now, if you want to actually deploy robots for general use, you need them to be able to respond to humans that are going to be, interacting with the robot, potentially intervening or giving corrections. And so in HiRobot, this is an open-ended instruction-following hierarchical vision language action model. They come up with this set of prompts that a VLA should be able to interpret and react to. And I'll have you look at situated corrections here. So in this one, Hi Robot is asked to clean up all the trash. It picks up something that isn't trash, and the robot interjects with that's not trash. The user interacts with that's not trash. And the robot says, oh, sorry, I'll put it back. And it puts it back and continues on cleaning up the trash. And then in the example just following that one is a user constraint. So Hi Robot is asked to make the user a sandwich. And as the robot is getting near the pickles, the user says, I'm allergic to pickles. And Hi Robot says, okay, I will avoid the pickles, and then continues making the sandwich. And then lastly is an open-ended prompt. So the user says, it's movie night. Can you get me some chips, Oreos, and a drink? And Hi Robot is able to go find some chips. It does find Oreos correctly, and it also finds and picks up a water bottle for the drink for the user. Sad, the water bottle. It needs a better drink. I tend to agree. So they break this down to kind of tackle these open-ended prompts. They look at this idea of having two levels of cognition. And this comes from Daniel Kahneman's book, Thinking Fast and Slow, if you've read that. But it introduces this idea of system one and system two. So system one is your automatic fast motor execution for known skills. And then system two is this deliberative reasoning about complex prompts, constraints, and feedback from users. So for the system two part, the reasoning part, they use a vision language model as a high-level policy, and that takes in image data. It outputs a robot's verbal response, and it takes in the user prompt and also generates this low-level language command. So this low-level language command goes into what they call their system one of a low-level policy in the form of a vision language action model. And that takes in the robot's joint states, images, and then outputs the actions needed. So what they found with this kind of two-level of cognition model is that if users modified a request mid-task, like saying leave the rest, Hi Robot is able to update low-level commands accordingly, whereas the baseline methods they compared to don't really make the right modifications. And they also find that Hi Robot has higher instruction accuracy and task progress in open-ended instruction following compared to some of the baselines they look at. So if you've been wondering whether or not any of this could be applied to mobile robots, it can. This is Navila, Legged Robot Vision Language Action Model for navigation. And in this work, they actually use their model on a humanoid robot and a quadruped robot and evaluate them both in real-world environments. You can see like a workspace and a home here. So if you look at this row, this robot, the humanoid, is given the instruction, move forward and exit the office area, and then turn right and stop near the blue trash can. And just given that language instruction and its onboard sensing, it's able to actually just go do that and stop by the blue trash can as the user requested. So how do they do this? They introduce a two-stage architecture for this. Now, in Hi Robot, we saw that the vision language action model was the low-level policy, the low-level executor. But here, they're actually using the VLA as a high-level reasoner. So the VLA here takes in the current view and a history of frames, and it outputs what they call a mid-level action command. These are things like move forward 75 centimeters, move to the left however many centimeters, move backward however many centimeters. Those get translated into velocity commands, and all of that goes into a low-level locomotion policy that's trained with standard RL methods. So for this particular work, they use proximal policy optimization to train that. But this buys you a few things. So first of all, it allows you to decouple the speeds of the VLA with the low-level action controller. So for quadrupeds or aerial vehicles or humanoids, you might need faster control to stabilize the platform than the VLA in their current state can actually provide for you at inference time. So you've managed to decouple those with this two-stage architecture, and you get continuous outputs as part of this without having to worry about which action head you're using on the model. You also get the benefit of having swappable low-level action controllers for different embodiments without needing to retrain the VLA. So this is exactly how they evaluate this model. They train a low-level locomotion controller for the quadruped and one for the humanoid, and they use the same VLA, just with the appropriate low-level locomotion policy for whichever platform that they're testing on. Okay, so at this point, we've seen that you can ground language in the robot's capabilities, and we've scaled vision, language, and action components. And we've looked at new ways to produce action outputs through denoising diffusion and flow matching. And that gave us smooth trajectories and continuous control. And then we looked at combinations of models where you can improve long horizon task success and improve task compositionality by chaining some of these models together. And lastly, we'll talk about chain of thought. So this is where we take some of the lessons from large language models that do some type of intermediate reasoning, and we try to apply that to VLAs for robots to make them reason a little bit before they take action. So if we use chain of thought, can we improve the robot's performance and allow it to reason before it takes action? So that's what they look at in this method. This is visual chain of thought reasoning for vision language action models. And here what they do is train the model to think visually before acting. And they do this by having the model generate a sub-goal image. So then, given that sub-goal image that the model generates, it conditions its action sequence on that sub-goal image and does this all in a closed loop fashion until it's able to complete the task that it's given. So they showed, they also compared to Octo and OpenVLA, which has now kind of become the standard in these types of tasks. And they were able to do better in all tasks on this emerging benchmark called Libero, which is starting to become like the benchmark for the robot learning type of tasks. But that's not the only way that you can have a robot reason before it takes actions. So in the last work, they used a sub-goal image to help the robot reason. But in this work, they actually force the model to reason through language before it takes action. So during the training stage, they use bounding boxes and motion primitives, which are extracted from the training data that they have. It's just like differences in end effector poses. And they use that to kind of ground the robot doing this reasoning and make the model go through these series of steps before actually executing its output actions. So following this example from left to right, you have the user that says, put the watermelon on the towel, and you have this input image. And the model extracts the task from that and says, place the watermelon on the towel. It comes up with a plan. And then it has to do some subtask reasoning for this first step. So it says the watermelon is the first object the robot needs to interact with. The robot is not yet close to the watermelon, so the robot needs to move closer. And it gets this subtask, move to the watermelon. So now it does this move reasoning where it says the watermelon is behind the robot, so it needs to move backward, and the action out of that is to move backward, and then the robot is able to actually do that and get near enough to the watermelon to finish the steps that it needs. So they also compare to similar baselines that we've seen, but one additional evaluation they do is what happens if a user gives a single interactive correction. And what they find is that they're able to boost the task success here by 48% just by having a user make a single correction. So if you're looking at this example, you just pick up any object that is not yellow. I think all of us have seen models struggle a little bit with this negative type of reasoning. So the model does struggle with this, and the user says, wait, there's a purple object in front of the arm. The model re-reasons and then is able to actually get to that object. And they actually show that you can improve the performance on all of the benchmark models with a single human interaction. So it's not just their model. And while this might seem like a little bit of a silly example, you can imagine that if just a single correction can actually help the robot reason and recover from a failure case, that's actually a pretty interesting result for anybody doing the human in the loop type of robotics.
What about the other people?
The not human in the loop, like me.
Yeah.
I mean, it's still cool, and maybe it works if I'm just debugging it and not actually doing the research.
Wouldn't this really suck for a human in the loop? Because then it's like the model forever is going to have to be told whenever there's a not. Like, find the object that is not yellow. And then next time it's find the object that's not a water bottle. And then the next time it's find the object. And it's every single time.
You want to find the purple object. Yeah.
No, but the upshot is that it doesn't actually solve the problem. It just means that the human's always going to be answering the same set of questions.
Can you not create a valuable data set from that alone and train a model on it though?
Is that the solution?
I don't.
If that's the solution, why didn't they do it?
I think personally that this probably came after when they realized that they didn't have as good a performance as RT2 in the no intervention case. And they were like, what would happen if we just corrected it while it was going? And they were like, this is an incredibly large margin with a very big number that reviewers will like.
But also not because of exams.
Yeah, anyway, I just think that this is like
Shallow.
it's like a bug. You know, they're basically like, if we have a human in the loop, they can fix our bugs. I don't know, it seems really weird. Okay, I mean, was there something specific about, so their method sees a 48% improvement as a result of intervention. The other methods don't have chain of thought.
Right.
That's the reason why.
Yeah.
Okay. Yeah.
Oh, this discussion is gonna be fun.
Looking forward to it. Where's the drink making robot? So
Margarita bot.
we've looked at the early models where we can use this vision language action paradigm, and then we looked at the new action paradigms where we get smooth trajectories, and we looked at hierarchical approaches where we're combining models, and then we looked just now at chain of thought reasoning and what you might be able to get from doing that chain of thought reasoning. And so now for the last part of this presentation, I want to move into talking about some open research questions in autonomous exploration using vision language action models. So we've seen a lot of work that looks at manipulators, lots of common household tasks, and we've seen one work where they actually deploy in a navigation style out on a real mobile platform. But there's a lot of open problems still if you want to deploy this on mobile robots and you want to use it for more planning or navigation type purposes.